Hello students, now we shall see the intermolecular reactions of olefinic bond, that is alkenes. So we have already seen the electronic excitations. We have 4 types of electronic excitations, but in case of this olefins or alkenes, it involves only 2 types. One is sigma to pi star and pi to pi star. So as the electronic excitation of sigma to pi star requires more energy, it is difficult to take place under normal condition. So it enables pi to pi star transition. So pi to pi star transition requires energy about 180 to 210 nanometer for non-conjugate olefins or 220 nanometer or more for the conjugated olefins. So formation of product depends on nature of olefin, nature of carbon-carbon double bond and excited state. So types of photochemical reactions which takes place in case of olefins are: one is cis-trans isomerism, that is geometrical isomerism. Second is cyclization reactions, or we call it as dimerization. And third one is rearrangement reaction of 1,4-diene and 1,5-dienes. So coming to the cis-trans isomerism, that is geometrical isomerism. So as you can see, so alkenes display geometrical isomerism due to the restriction rotation about carbon-carbon double bond which exists in 2 isomeric forms are called cis and trans. So one is, as you can see, trans form, where the alkyl groups are on opposite sides. In case of cis form, alkyl groups are on same sides. Usually trans isomer is thermodynamically more stable because of less steric hindrance, because alkyl groups are on opposite sides. Interconversion of these geometrical isomer of alkene can be carried out by thermally, catalytically or photochemically. So when these thermal and catalytic methods are used, so stable isomer is formed, but photochemical reaction give a mixture that is which is in which cis isomer is richer in percentage. So irradiation therefore provides a means of converting trans alkene to the cis isomer. So photoisomerism, that is by photochemical reaction, alkenes can be carried out through 3 types. One is direct radiation, photosensitizer and catalytic process. So through direct radiation we consider an example of still bean. So direct radiation of solutions of either cis or trans still bean yields a constant mixture consisting of 93% cis isomer of still bean and 7% of trans still bean. So as you can see in the reaction, C6H5CH double bond CH C6H5. So an arrow that is H mu, so which gives a cis isomer. So where both C6H5 groups are on same side, so it is the product gives a mixture of both cis and trans. Cis is 93% and trans is 7%. So initial absorption of light either of these is rapidly followed by interstate conversion or intersystem conversion to the respective triplet states. Photoisomerization then occurs via interconversion, that is IC, or a common triple intermediate. So as you can see in this reaction here, so we have taken both cis-stilbene, whether it is cis-stilbene or trans-stilbene. So when they are irradiated with, when it undergoes a photochemical reaction, so first the cis-stilbene and trans-stilbene are converted to the singlet excited state. So these are again converted to the triplet excited state, where cis-stilbene and trans-stilbene are in equilibrium. So in the triplet excited state, it gives rise to the mixture of a 93% of cis-stilbene and 7% of trans-stilbene. If instead of direct radiation, if you go for a photosensitized isomerization, that is using an photosensitized reaction, a photosensitizer. Photoisomerism also occurs in presence of photosensitizer. A sensitizer absorbs the radiation, undergo vibrational relaxation and intersystem crossing to a stripper state, and then take part in an energy transfer process with alkene. So as you can see the mechanism here. So triplet state, mercury in its triplet state is taken as a photosensitizer. So when it reacts with a, any other like olefins, so that gives rise to an excited state of olefins. So this undergo a 90 degree rotation. When it undergoes a 90-degree rotation, so it gives rise to a new structure or a new state of molecule. This state is called as phantom state. So this undergoes deactivation and gives rise to a constant mixture of 53% and 47%. So this is for any alkene or olefin. So if you use a stilbene, so here also you can expect a 93% of cis isomer and 7% of trans isomer. So here mercury acts as a photosensitizer. The mercury, which is in triplet state, transfers its energy to alkene and returns to the ground state. Alkene absorbs energy of mercury and get excited to the higher energy level. Pi to pi star excited state is minimized by twisting the structure around carbon-carbon single bond by approximately 90 degree. This distorted configuration of excited state is called phantom state, in which distinction between cis and trans isomer is lost. So more of trans isomers is converted into cis isomer by using suitable filters. The process of converting of more stable trans form into a less stable cis form of higher yield through transition state is called optical pumping. So this is very important. The process of converting a more stable trans form into a less stable cis form of higher yield. So if you want, so that means we are expecting an usually trans state is thermodynamically stable, but instead we are getting a cis form, so which is at higher percentage, we want higher yield, and this is called as optical pumping. So here you can see the mechanism involved in this photosensitizer. So using a stilbene, which is in a trans isomer of stilbene is taken, which gives rise, it is in a ground state, singlet ground state. So it goes to the singlet excited state. So singlet excited state when it is rotated in 90 degree, you will get a twisted state structure. It is called phantom state. So this will gives rise to a cis isomer. That is, trans isomer absorbs light at higher wavelength and get excited to singlet state, that is S1, where we absorb saturation bond. At this rotation about 90 degree gives a twisted non-planar structure. So on deactivation, cis isomer is formed. So it can be done in presence of photosensitizer like benzophenone or acetophenone. So transformation is as you can see in this reaction mechanism. So benzophenone, which is in singlet ground state, absorbs energy. It undergoes a photochemical reaction. So electrons get excited from non-bonding orbital to the, that is n to pi star, non-bonding orbital to the anti-bonding pi orbitals. So this gives rise to an singlet benzophenone, that is an excited singlet state. So this undergoes, instead of going to the triplet state directly, it undergoes an intersystem crossing that gives rise to an triplet state. So this triplet state benzophenone molecule now reacts with the singlet ground state of stilbene. It transfers its energy to the stilbene. Now stilbene takes up energy and gets converted to the a triplet state, and benzophenone comes back to the singlet state. That is, benzophenone absorbs light and undergo n to pi star transition. It converts into singlet ground state to the singlet excited state, followed by intersystem crossing. Now it acts as a photosensitizer and transfers its energy to the stilbene. Triplet state of sensitizer acts as donor, and trans stilbene in the ground state acts as acceptor. So now we can see stilbene. We have got a cis isomer of 93%, trans isomer of 7%. So it also undergoes a catalytic method. Photoisomerization also can be achieved in presence of catalyst like bromine. So here you can see a halogen atom absorbs photon and gives the radical. Then radical adds to alkene, forming intermediate radical where bonds can rotate, so that alkene excited state does not take part. So this is all about the cis trans isomerism in alkenes or olefins. So one is from the direct method, another one is from the by using a sensitizer, that is benzophenone. So in all the cases, so you will get an 93% of cis isomer and 7% of trans isomer. So next, coming to the cyclization reactions. So you can see cyclization reactions, they are also called photodimerization of olefins. Photodimerization of olefins. So this reaction involves interaction of an excited triplet state with the ground state olefin. The reaction can be inter or intramolecule. So here you can see in the reactions borane, when it is absorbs light in presence of a stone, it gives rise to an acyclic product, which is a dimer. So if we can see here, it also undergoes intramolecular, as we have said, it is intermolecular or intramolecular. It undergoes intramolecular. Norbornadiene is an intramolecular reaction. So when it absorbs light in presence of sensitizer, it gives rise to an quadricyclane. So you can see the mechanism. So cyclization of norborane. So alkenes undergo dimerization through pi star transition in excited state. Acetone is used as a sensitizer. The triplet donor acetone transfers its energy to the ground state alkene molecule and returns to the ground state. The alkene molecule in the triplet excited state will react with another alkene molecule and forms a dimer. An interesting case is that there may occur an intramolecular reaction between two propylene double bonds in a molecule forming an isomeric substance. So here in the mechanism you can see, so this which is in the singlet ground state, it absorbs light, a dimer, that is norborane. Then it goes to the singlet excited state, and by intersystem crossing it forms a triplet excited state. So by pi to pi star excitation, so this forms a mixture of again two isomers cis and trans. Cis is at 8% and that is a major product, and minor product is 12%. So in case of so below here you can see this is an intramolecular reaction. So we have used norbornadiene, so it also goes to the singlet from ground state to the singlet excited state. As it undergoes intersystem crossing, it forms a triplet excited state, and again it gives rise to an quadricycline. So here another example, a mixture of three dimers is formed on sensitized irradiation of butadiene. So in case of intramolecular reactions of olefinic bond, the other one is rearrangement of 1,4 and 1,5 dienes. So irradiation of 1,4-diene or 3-phenyl alkenes often lead to vinyl cyclopropane. So reaction is as simple as, say, as you can see, we have a 1,4-diene. So 1,4-diene gives rise to, that is 1,4-diene rearranged into vinyl cyclopropane in presence of light is called as dipymethane rearrangement. This is also called as dipymethane rearrangement. So irradiation of 1,4-diene often lead to vinyl cyclopropane through 1,2 shift. These reactions are termed as dipymethane rearrangement, also known as Zimmermann reaction. So you can easily say 1,4-diene rearranged into vinyl cyclopropane in presence of light is called as dipymethane rearrangement. So in the mechanism you can see the bonds which are in case of 1,4-diene, the breaks, it absorbs light in the presence of sensitizer. The pi to pi star excitation happens. So as you can see here it forms a diradical. So first bond formation between carbon 2 and carbon 4 happens. So and gives rise to a diradical. So this diradical, in case of diradical, bond breaking between C2 and C4 happens and gives rise to an vinyl cyclopropane. So it is a very two-step mechanism. So which is here the two bonds. So one bond breaks by absorption of light, and also other bond breaks, and when it breaks it forms the first bond formation between carbon 2 and carbon 4 happens. So next it forms a diradical. This diradical, in case of diradical, bond breaking between C2 and C4 happens and gives rise to a vinyl cyclopropane. So methane reaction generally occurs through excited singlet state obtained by direct irradiation, whereas triple pathway is accessible only using triplet sensitizers due to poor intersystem crossing efficiencies of alkenes. So some more reactions. So regarding methane is also given. So these are reactions of or intermolecular reactions of olefinic bond. One is we have seen cis-trans isomerism, there is geometrical isomerism of steel beam, and cyclization reaction or photodimerization of olefins. We have seen nor-borane and nor-bornadiene. So and third one is rearrangement of 1,4-diene. So this is about intramolecular reactions of olefinic bond.